meter amp divided by 4 pi. I is 10 amps. DS is 0.5 millimeters. And then okay, so all this works out to the 4 pi cancels. That is 10 to the 10 to the minus 3, 10 to the minus 10, and this is 10 to the minus 4, so you get 10 to the minus 6. And this is a magnetic field, so it'll work out in Tesla. And this is 10 times, that's 5 3/5, so you get 3 over 25. So we'll just write it like that, 3 over 25 microtesla. All right, so what we have found is when the current flows in this direction, the magnetic field due to this small element, 0.5 millimeter is that much. Remember, due to that little element is coming out of the sheet, it's perpendicular to the sheet, and it's 3/25 microtesla. And if you want to find the total field at this point, you'd have to sum the field due to all these guys. You'd have to do that integral, okay? All right, so in this shows a current loop consisting of 2 concentric circular arcs. So there's a current flowing like that. And you want to find the field at this point. Where does this current loop produce a field? It produces a field everywhere. You would be very hard pressed to find the field at any of these locations. At this one particular point, the field is easy to find, and that's where we're going to find. Okay. The field at this point is the field due to this guy, plus the field due to this guy, plus the field due to this guy, plus the field due to this guy. What is the field due to this guy at this point? 0. So these two guys produce 0 fields. Only this guy and that guy produce a field. And remember, we know the field due to a circular loop. Well, we'll calculate that. So, and then you'll get an expression. So, determine the magnetic field at point P. Okay, so here's the expression, the field due to a small element. We just saw that 4 pi. Okay, so this element ds, there's r hat. Okay, so this element And again, you can stick your fingers, so you're always using your right hand. If you stick your fingers in the direction of the current, your thumb points in the direction of the magnetic field. Okay, so this guy, and also you can see it from here, ds cross r hat, if you turn the screw this way, the field will be coming out of the sheet. Okay, or an easier thing is stick your fingers in the direction of the current, and your thumb points in the direction of the field. So this guy will produce a field coming out of the sheet, and by similar argument, this guy will produce a field into the sheet. Okay. Okay, now, so that's the field produced by this guy. So if you want to find the field produced by the whole thing, you'd have to integrate it, except that, see, ds cross r hat is just ds, they're perpendicular to each other, sine theta is, sine 90 is 1. So the magnitude of this magnetic field is mu naught 4 pi I ds over r squared. Okay, now when you integrate this, r is constant, I is constant, all you're doing is adding up all these ds, the small arc elements. So that's 1/4 of the circumference. Okay, so the net field is equal to field out minus field in. Out is the field due to this guy coming out of the sheet, and field in is the field due to this guy, which is going into the sheet. And the field out is mu naught 4 pi I, and this arc is 1/4 of the circumference, and the radius of that is a. So 1/4 of the circumference is 1/4 2 pi a divided by a squared. And then minus mu naught 4 pi I 1/4 2 pi b. 1/4 of this circumference is, the radius of that is b, divided by b squared. Okay. Mu naught 4 pi is common, I is common, and what you have here is 1/4, that's 1/2 a. Oh, 1/2, no, there's a pi as well. Pi over 2a. So okay. So, and then this pi will cancel with that pi, and you'll get an 8. So the net field is so the field is coming out of the sheet because this wire is closer. Okay. Okay, they say the magnitude of the magnetic field 50 centimeters from a long thin straight wire. So when they say long thin straight wire, they mean they're essentially telling you, think of it as an infinitely long straight wire. Okay, is 8 microtesla. What is the current through this long wire? So again, here's and what is the direction of the fields? The fields are concentric circles like that. And the strength of the magnetic field is given by mu naught I by 2 pi r. Okay. So they give you the strength of the field and they were asking you to find the current. So 8 microtesla, 2 pi r, r is 0.5 meters. And mu naught is 4 pi times 10 to the minus 7. Okay, the Tesla cancels, the meter cancels, and you get ampere on top. All right, so you get 10 to the minus 1, which will bring up here and make that a 5. So it's 8 into 2 pi into 5 divided by 4 pi. So you get 2, 4, 20. 20 amps. Okay. So you see a 20 amp current. So here's a 20 amp current. At this distance, half a meter away, it's producing a micro Tesla field, which is this thing is the field in the Earth's magnetic field is 10 to the minus 4 Tesla. So a 20 amp current is producing a field that is 100 times weaker than the Earth's magnetic field. Okay. So remember, in a MRI machine, how strong of a field do you have to produce? Yeah, so 2 to 3 Tesla. You got to produce a field 1,000,000 times stronger than that. So you produced a field of a micro Tesla here. You got to produce 1,000,000 times stronger field. A long straight horizontal wire carries a left to right current of 20 amps. If the wire is placed in a uniform magnetic field of magnitude 4 times, so this is the Earth's magnetic field that is directed vertically downwards, what is the resultant magnitude of the magnetic field 20 centimeters above the wire? Okay, so we'll calculate one of them. Okay, so here's a 20 amp current. If the wire is in a uniform magnetic field of magnitude directed vertically down, so it's in the presence of a magnetic field B naught equal to 4 times 10 to the minus 5 Tesla. So you're somewhere near the North Pole, okay? So here's a horizontal wire and you're near the North Pole where the magnetic field is pointing straight into the ground, okay? What is the resultant magnitude of the magnetic field 20 centimeter below the wire? So we'll find, okay, this wire will produce a magnetic field. And what is the direction of the magnetic field this guy produces? You stick your thumb in the direction of the wire, gives you, so this guy will produce a field into the sheet, okay? Above, it'll produce a field outside the sheet, okay? So it'll produce a field that, and in here, it'll produce a field inside. All right, so what we'll do is, so now, here's the Earth's magnetic field and here's the field produced by the wire. And these two guys are perpendicular to each other. Okay, so let's find the strength of this field and then we'll find the net field. Okay. Use your right hand, not your left hand.
Reverse the problem.
Okay.
The problem is what it is. It's the sign. It is complicated, yes. But if you're writing from your right hand.
So you put your pen down. But anyway, all right, so let's find the magnitude of the field produced by this guy first. So B is mu naught divided I times 2 pi R. Okay. So mu naught is 4 pi times 10 to the minus 7. The current is 20 amps. And we already know the magnitude of this thing. Remember, the 20 amp current produced 8 microtesla, but here you're closer, so 20 centimeters. So this works out to, so that's 2, that makes it 10 to the minus 6, and 20, so 2 times 10 to the minus 5, right? So this current is producing a magnetic field 20 centimeters away. It's producing a magnetic field that's comparable to the Earth's magnetic field. Okay. All right, so now we'll draw a different diagram. So now you have a net field B naught in this direction. So now we're doing it as side view, and this is B is 4 times . Okay, so what I've done is now I'm looking at it from this view. This field was in that direction and that field is in this direction. That's what I'm drawn. Okay. So the net field will be in this direction, and this. So the, so the strength of the net field is that much, and it's pointing in this direction. And if you want, you can calculate the angle, theta. Okay. Okay, so this problem says 2 long straight wires are parallel and 10 centimeters apart. One carries a current of 2 amp and the other of 5 amps. If the two currents flow in the opposite direction, okay, when the currents are in the opposite direction, the wires repel each other. Okay. And here's how you quickly find the force. Okay, so the force on this guy will be in this they repel each other. Okay, this guy, so you can find from first principle, this guy will produce a magnetic field at this point. Again, stick your wire out into the magnetic field produced will be in that direction, and V cross B will be a downward force. Okay, so V cross B will be a downward force. Anyway, if the two currents flow in the opposite direction, what is the magnitude and direction of the force per unit length? So now we'll find the magnitude. The direction is their repulsion. So part B, it's if they're flowing in the same direction, then the force is attractive. Okay, the magnitude will be the same. So force per unit length is given by mu naught I1 I2 divided by 2 pi r, the distance between them. Okay, so let me make sure of the expression. So there's the expression. Force per unit length is that. Okay. Tesla meter amp. The two currents are 2 amps and 5 amps. 2 pi 0.1 meter. Okay, that makes it 10 minus 6, 2, and then 10 minus 5. 2 into 10 minus 5 Newton per meter. Okay. So the magnetic force is pretty small actually. Okay. A flat circular loop has 20 turns. The radius of the loop is 10 centimeters. And the current through the wire is 0.5 amps. Determine the magnitude of the magnetic field at the center of the loop. Okay. So they want you to find the magnetic field at the center of the loop. So we'll use this expression. So this is the expression we'll use. So this we'll use. Okay, here's the expression. I like to write it like this: mu naught divided by 2 pi. So this is equal to mu naught mu times 2 pi r squared plus c squared. Okay, so we'll use this expression. This is the strength of the magnet. Okay. Okay, so here's the loop. We're finding at the center, Z is 0 there. So all you do is R. So B is mu naught N I A. N is the number of loops of wire. I is the current. A is the area of the loop. Divided by 2 pi times R. So Z is 0, and this would become R cubed. Okay. So So here's the expression for the magnetic field at the center of a circular loop. Twenty turns. So that makes it 10 minus 6. That makes it 10, 2 pi. 10 times 2 pi, 20 pi. So the magnetic field is 20 pi into Tesla. So the field due to a circular loop of 20 turns carrying half an amp current at the center is 20 microtesla. This problem says two flat circular coils, each with a radius r and wound with n turns, are mounted along the same axes, so they are parallel and a distance d apart. Okay, so what is the magnetic field at the midpoint of the common axes? If a current I flows in the same direction through each coil. Okay, so I is flowing through there. Okay. Again, so this guy is producing a field along the axis, so you stick your fingers out in the direction of the current and your thumb points in the direction of the magnetic field. So this guy's, at this point it's producing a field like that, at this point it's producing a field like this. So we'll call this coil 1, coil 2. So at this point B1 is in this direction. And B2 is also a field in that direction. Okay, so they are producing a field in the same direction. Okay, and so when the field currents are parallel, the fields add up, and if the currents were in the opposite direction, the fields would cancel. Okay. All right. So, and the expression is again due to a current loop. We saw the expression for a field. B is mu naught by, what is it? Is it 2 pi or 4 pi? 2 pi. Mu over the field at this point is r square z square to the power 3/2 strength of the magnet times that. So the field due to this guy, z would be d by 2. Okay, and since the field are in the same direction, the net field is equal to B1 plus B2 equal to 2B1 equal to 2 times B is mu naught, B1 is 2 pi Ni area r square d by 2. Okay. Okay, they tell us n turns, current I, and that's all they tell us. So there's the expression. Okay. N turns, current I, area of the loop, area would be pi r squared. So we'll put that in there. So okay, and then we'll clean this up. The pi cancels, 2 cancels. Okay, so mu naught NIR. Okay. That's the field at the center. Okay, so again, notice in all the calculations, we're calculating fields at very special points. See, the field at any other point will get messy. And can you find the field at this point? We have a formula for fields at this point. At non-axial points? No. Okay, so we are calculating fields at very special points. This says a superconducting wire of diameter 0.25 centimeter carries a current of 1,000 amps. What is the magnetic field just outside the wire? Okay, so by the way, they use these superconducting wires when they're passing currents between cities. So they use these to minimize losses. So here's a wire. And remember, inside the wire, so let's say the current is coming out of the sheet. Okay. You guys remember? What is the magnetic field at the center of the wire? 0. And then as you come outside the wire, the field is getting stronger. And it's the strongest at the surface. Okay. And at the surface, the field strength is mu naught I times 2 pi r, the radius of the wire. Okay. So that's the magnetic field just outside. The strength, the magnitude of this field. So it's the current is 1,000 amps. 2 pi r is 0.25 centimeters. 0.25 centimeters is 3 millimeters. That then. Okay, that makes it 10 to the minus 5, 10 to the minus 2, 2, and this is 10 minus 2, so that cancels that. So that's 2/25. So the magnetic field just outside that wire is 2/25 of a Tesla. Okay. Okay, so roughly about, so the Earth's magnetic field is about 10 to the minus 5, so about 1,000 times stronger. Okay. If a current is 2 amps, how many turns per centimeters must be wound on a solenoid in order to produce a magnetic field of 2 millitesla within it? Okay, so a solenoid is a cylindrical object, and you're winding wires like that to produce a uniform field. Okay. Remember, you did this for for a particle detector. You did this for MRI machines, but this is a very small field. Okay, and the strength of this magnetic field, B, is mu naught n. Little n is the number of turns of wire per unit length times I, the current. Okay, what is it that they want to us to find? So they give us the current, how many turns per centimeter. Okay, so they're asking us to find n. N is that B is 2 into 10 to the minus 3. Okay, so the Tesla will cancel, ampere will cancel, and what you'll get is 1 over a meter. Okay, so that's how many turns you have per meter. The 2 cancels, and so that's 10 to the 4 over 4 pi per meter. And 1 meter is 100 centimeters, so 8 per centimeter. 8 turns per centimeter. A centimeter is about that much, so 8 turns of wire per centimeter. So this problem says a toroid is a donut with wire wrapped around it. It carries a current of 20 amps. Its inner and outer radii are 8 and 9 centimeters. What are the values of its magnetic field at these various values? Okay, I'll calculate for one radii. So here's a cross section of the toroid. So we'll say the wires are wrapped around like that. So these wires are going into the sheet, and this is coming out of the sheet. So this is a current coming out. This is a current going into the sheet. Okay, and so to figure out the direction of the current, so okay, this current is going like that. Point your thumb out, and the magnetic field will be pointing like this. Okay, so the magnetic field lines are going like that. Okay. Now, so what we are going to do is, so it turns out that the field is stronger here, and as you go further, the field gets weaker. Okay, except that if the size of this is small compared to to the radius of this thing, then the field can be considered uniform. But here, so the field is stronger here and weaker there. Okay, so all right, what we'll do is we'll use Ampere's law. Mr. Ampere tells us this line integral is equal to mu naught times I, the current threading through this. Okay, so what we're going to do is we're going to do the line integral along here. Okay, so at a constant radius, and so this line integral will be easy. The magnetic field is constant, so this line integral is, if r is the radius, okay, so the line integral is b times 2 pi r, and as long as you're inside this, what is the total current threading through here? The sum of all these currents. So each of these wires is coming in out of the sheet. So the total current is I. A toroid has 250 turns of wire. So there's 250 wires coming out. So it's 250 times I. Mu naught times N times I. Okay. So B is mu naught N divided by 2 pi R times I. Okay, so, and we'll calculate it for 8.9 centimeters. Okay, so we'll calculate the magnetic field at this edge, at the outer edge. We'll do for R equal to 8.9 centimeters. And if you look up your notes, N divided by 2 pi R. So if, again, like I said, if this dimension is small, 2 pi R is the circumference, N divided by that gives you the number line density, which was denoted by small n. Okay. I, the current is 20 amps. By 8.9 centimeters. Okay, 2, and what you get is 10 to the minus 5, 10 to the minus 3. We'll do 10 to the minus 3, 10 to the minus 3, 2 into 2.5 into 20 divided by 8.9 Tesla. Okay, so this is the field at the outer edge. At the inner edge, instead of 8.9, we'll do 8.1. So that would be, okay, so this is the outer edge, and the inner edge, the field is 12.35 millitesla. Okay, so that's the difference. Yeah. All right, guys, so that finishes